a bit of an outsider to the singularity debate, the singularity literature. I'm a philosopher, in particular a philosopher of probability. I'm interested especially in the foundations of probability. But I think there are various connections between what I do and the singularity, and I'll try to bring some of them out later on in the talk. It came as a bit of a surprise to me that there's this theme that I keep returning to in my philosophical work, the improbable. It shows up in my work on conditional probability, on independence, on decision theory, counterfactuals, Pascal's wager, imprecise probabilities, and elsewhere. And I'll revisit those themes today, but I'll make some new connections between them that I haven't done in my previous work. And then there'll just be some new stuff, and in particular, as I say, some connections to the singularity. So it might start to look like an obsession of mine, this concern with the improbable. I prefer to call it my fascination. But I think it should be your fascination too, or so I'm going to argue. Because I think that improbable events have an important impact, important ramifications for science, for philosophy, for daily life, and yet because they're improbable, we're liable to neglect them or to downplay them. So I hope that you'll join me in my fascination, and this will be my plea for the improbable. Let me begin the plea by looking at the improbable as it arises in some places in science and in philosophy and elsewhere, beginning with a completely familiar case, statistical significance testing. You probably know how this goes, but a quick reminder. We want to pit a null hypothesis, call it H0, against an alternative, call it H1. We gather some data. We reject H0 if, by its lights, data at least as extreme as that observed is to improbable. Typically, the threshold for improbability is 0.05 or 0.01. And this reminds us of something that should have been obvious, but it's worth highlighting. Improbable must be relativized to a probability function, and more generally to a probability space. At the other end of the spectrum, as well as data fitting a given hypothesis too poorly, it can also fit it suspiciously well. There's Mendel and Fisher. And Fisher accused Mendel of cooking the books in the published results of his Plea experiment. So, looking at the published data, Fisher figured out that the probability that by chance alone the data would fit Mendel's theory of heredity that well was about 3 in 100,000, and so it seemed that Mendel had rigged the data, or in Fisher's unforgettable phrase, had sophisticated it. Cournot is famous for this principle. An event of small probability singled out in advance will not happen. Right? Will not happen. This guy knew something about probability. Cournot's principle was advocated by Kolmogorov. Borel, who also knew something about probability, was so enthusiastic about Cournot's principle, he said, the principle that an event with very small probability will not happen is the only law of chance. And the principle still has some currency, having been recently rehabilitated and advocated by Schaefer. This is Glenn Schaefer, as in Dempster-Schaefer theory, if you know about that. But I think that Aristotle got it right, and Tim Minchin got it right. It's likely that unlikely things should sometimes happen, said Aristotle. And how did the Tim Minchin quote go? So the problem was that one of underestimating the number of things that there are. If you've got a lot of things, there'll be a lot of improbable things among them. In fact, I think Aristotle understated it. Improbable things happen all the time. So much for Cournot's principle. Remember this guy, displaying his characteristic sparkle and easy charm. And he's famous for the so-called 1% doctrine. He said, if there's a 1% chance that Pakistani scientists are helping Al-Qaeda build or develop a nuclear weapon, we have to treat it as a certainty in terms of our response. The idea here was that the USA had to confront a new kind of threat, that of a low probability, high impact event. Well, Cournot effectively rounds down the event's low probability, treating it as if it's 0. Cheney rounds it up, treating it as if it's 1. Now, to be sure, Cournot doesn't tell us exactly what the threshold for improbability is. Cheney doesn't tell us just how widely his 1% doctrine is applicable. Still, whatever intuitions they're appealing to, they're diametrically opposed. Now, turning to engineering. I have a friend who works at the Jet Propulsion Laboratory. His job is to calculate the probability of mission failure for missions like the Cassini spacecraft. That was the mission to Saturn. He calculated failing. That was about 1.1 times 10 to the minus 3, about 1 in 1,000. According to the US Nuclear Regulatory Commission, the probability of a severe reactor accident in 1 year, this one's a bit different. This is imprecise. Now we'll think of the probability here as interval valued, and it's about 1 in a million to about 1 in 100,000, and slightly surprisingly, maybe even improbably, that number 1.1 keeps appearing. Let's turn to philosophy. Improbable events have earned their keep in philosophy. A concern with improbable events has driven philosophical positions and insights. Let me begin with one from the so-called lottery paradox, which puts pressure on the so-called Lockean thesis. So we want to connect two things, belief and degree of belief. So I believe, so do you, that Melbourne is in Australia. I also have various degrees of belief. I don't know, I give pretty high degree of belief that it'll be sunny in Melbourne tomorrow, let's say 0.9. But that's not quite the same thing. It's not that I outright believe that it'll be sunny in Melbourne tomorrow. So the issue is, how do we bridge between this degreed notion and binary all or nothing belief? The Lockean thesis says belief is just sufficiently high degree of belief. Degree of belief above a threshold. Well, let's set the threshold. Let's take, say, 0.95 as the threshold. For a given threshold, consider sufficiently large lottery, let's say 100 tickets. Your degree of belief that ticket number 1 will lose clears the threshold. It's at least 0.95. So by the Lockean thesis, at that threshold, you believe that ticket number 1 will lose. But hang on, that's true of ticket number 2. You believe that it will lose. ... all the way up to the final ticket, ticket number 100. You believe that it will lose. But you believe that some ticket will win. In fact, let's agree, you're certain of that. Seems like you have inconsistent beliefs. And something's gone wrong, but it seems we can't fault you. It's not like you made any mistakes. Maybe we should fault the Lockean thesis, this bridge between degree of belief and outright belief. For the Lockean thesis to be plausible, the putative threshold for belief must be high. It's 0.95 in my example. Accordingly, the probabilities involved in the lottery paradox will be small. They were 1 in 100 in my example. Lotteries cast doubt on Cournot's principle. So imagine each of the ticket holders staring at their ticket, wondering whether it will win. One of them will, and when it does, that's a low probability event occurring, contra Cournot's principle, at least at that setting of the threshold, but just increase the lottery so that there's enough tickets to be the counterexample to Cournot's principle. Okay, another philosophical example. Vogel has an argument for skepticism about knowledge. It seems like I know where my car is parked right now. I can remember where I left it. But hang on, I don't know that I'm not one of the unlucky people whose car has been stolen during the last few hours. I know the statistics on crime a little bit. I know that there's a positive chance non-negligible chance that my car's been stolen. In which case, I don't know where my car is parked. In fact, I don't even know if it's parked. For all I know, the car is being joy-ridden around by the thief. It seems I can't rule that out because there's a positive chance of it having happened. Now, in this example, we're liable to neglect the probability that undermines the knowledge claim because it's so small. Because the thing that's claimed to be a piece of knowledge is so probable. Take something far less probable. No one in their right mind could say that they know that Geelong's going to win the premiership this year. David Dow is a Geelong supporter. And that's because the probability of it happening is so low. Consider a much higher event. Reluctantly, I have to concede, even I don't know that Collingwood will win, even though the probability is so high. It's because there is some chance of it not happening, and that's enough to undermine the knowledge claim. But anyway, you see how the Vogel point is supposed to generalize. Just even tiny chances of the claimed bit of knowledge not happening suffice to undermine the claim to knowledge. All right, so far I've been, I hope, warming you up. I hope you have at least a tacit understanding of my subject matter, the improbable. Now let me be a little bit more specific about what I mean. I will count as improbable these propositions or events. First, those that have probability 0. Always improbable, no apologies, no retractions, they are just improbable. Second case, those that have infinitesimal probability, and I mean this in the technical sense, positive but smaller than every positive real number. Always improbable. Third case, those that have small positive real valued probability. Well, what's small? That's vague, it's context dependent. But we know clear cases when we see them, and my cases will be clear. I'm sure you won't begrudge them. You know, things like 1 in a million, small probability. And then this one, maybe you wouldn't think of at a first pass. I'll also count as improbable events that have imprecise probability, thinking of that as interval valued, with an improbable upper limit in one of the previous senses. All right, well, there are various peculiar properties of low probabilities, and I want to use them to do some philosophical work. So I want to go through these properties systematically, showcasing each of them with a philosophical application, a philosophical payoff. All right, so this is where I'm just going to march my way through the taxonomy, starting with the probability 0 events. And much of what's philosophically interesting about probability 0 events derives from interesting facts about the arithmetic of 0. 0 is just the weirdest of all the numbers. And it's weird in completely familiar ways. School children can tell you about the ways in which 0 is weird. But I say each of its idiosyncrasies motivates a deep philosophical problem. And these will be, I hope, the payoffs. Some of them are familiar. Well, starting with problems especially for Bayesian orthodoxy, and coming from the philosophical point of view, I mean by this, for a start, the thesis that beliefs come in degrees, and I gave you an example, my degree of belief in a sunny day in Melbourne, 0.9. And these degrees of belief are rationally required to obey the probability calculus. So I'd better give 0.1 to not sunny day tomorrow, and so on. And they update by a rule called conditionalization, and I'll say more about that shortly. And we could add, they combine with utilities to determine expected utilities, which are measures of desirabilities of options, how good the options are, and more on that shortly. Yet I think the future of AI is a Bayesian one, so I'm generally a friend to Bayesianism. It's just, I think it hasn't got some of the details right, and that's what I'm going to turn to here. Now you might say we could reasonably dismiss probability 0 events as don't cares if we could be assured that all probability functions of interest assign 0 only to impossibilities. So let me call that property open-mindedness. So for anything that's possible, the function gives positive probability. Maybe very small, but not zero. It only zeroes out something impossible. Let's call that open-mindedness. And I think that open-mindedness is part of the folk concept of probability. You know, if you ask people on the street, they'll agree to things like, if it can happen, then it has some chance of happening. In fact, I've done a survey of this. I did an empirical study. I asked 2 of my friends and they agreed. So I took that as emphatic confirmation. So think of, say, tossing a coin. We all know the coin can land heads, it can land tails. Well, it can land on its edge. Well, that must have some probability. If we get even a bit more imaginative, I mean, maybe there are weirder things that could happen to the coin. In fact, maybe it's possible for the coin to spontaneously transmute into a sheltie while it's in mid-toss. Well, if that's possible, if it can happen in some sense, then still its probability is positive, presumably small. Open-mindedness. Well, open-mindedness has support from some weighty philosophical figures. This is David Lewis, the great David Lewis. But we'll see how much trouble probability zero but possible events cause. It'd be nice to banish them. You just don't have to worry about them. You can stay open-minded. Only impossibilities get probability zero. Well, that would be nice, but it doesn't seem like it's true. There are apparently events that have probability zero, but that can happen. And what a great previous talk from Burkhardt. This is exactly the case that I'm going to give too. A fair coin is tossed, make it infinitely many times. This is like Rosencrantz and Guildenstern are dead writ large. And the probability that it lands heads every time, heads, heads, heads. So it's even more boring than that movie. Just imagine that going on infinitely long. That event has probability zero. Well, we'll revisit this claim later, but for now, let's just assume it. I need a snappy example of a probability zero event. I think there are others. Let it be this one for now. Here's another one. A dart is thrown at random at the 0-1 interval of the real line. Here's a representation of that. And we'll make the usual assumptions that probabilists like to make. The dart is infinitely thin-tipped, so it'll land exactly on a point, a real number. The toss is fair in the sense of not being biased to any part of the interval over any other. So let's do the toss. Suspense mounts. Here comes the dart. Whoa. I enjoy that so much. Yes, it only always lands on the same point. So, various non-empty subsets of this interval get assigned probability zero. For a start, all the singletons, just the single points, like the dart landing just where it did, 0.37 or whatever it was, probability zero. All the finite subsets, probability zero. Indeed, all the countable subsets, like the rationals. And in fact, even various uncountable subsets, Cantor's ternary set. You know that. Okay? So, there are various non-trivial and interesting examples of probability zero events, and they create various philosophical problems, each associated with a peculiar property of the arithmetic of zero. So this is where I'm now going to go through these weird properties of zero, familiar to school children, and then for each of them, an interesting philosophical payoff, starting with the fact that you can't divide by zero, as school children can tell you. And this creates trouble for the usual ratio analysis of conditional probability, which you'll see in every textbook. Probability of A given B is this ratio of unconditional probabilities. Well, with a proviso, you can't divide by zero. The denominator had better be positive. What's the probability that the coin lands heads on every toss in that infinite experiment, given that the coin lands heads on every toss. And I say 1, surely. But the ratio formula cannot deliver that result because the bottom line, the probability that the coin lands heads on every toss, is 0, and you can't divide by 0. Now that quickly turns into a problem for the Bayesian updating rule of conditionalization, which is defined in terms of it. So here's the idea. Suppose that your degrees of belief are initially given by a probability function, P initial, and that you become certain of a piece of evidence, call it E, nothing stronger than that. So conditionalization says your new probability of something like X is your initial conditional probability, X given E. But again, there's that proviso. E had better have positive probability. Suppose you learn that the coin landed heads on every toss. What should be your new probability that the coin landed heads on every toss? I say 1, surely. But this conditional probability is undefined. You can't divide by 0. So conditionalization so defined in terms of that ratio cannot give you this advice. All right, now to be sure, there are some more sophisticated methods for solving these problems to do with the 0 on the bottom line. And various authors have written on this topic, so have I. I'm fond of so-called Popper functions. These are primitive conditional probability functions. Instead of axiomatizing unconditional probability, the way Kolmogorov did, and then later on defining conditional probability as a certain ratio, just go straight to the conditional probabilities. And now there's no obstacle to having them, even with a condition whose probability is 0. And Kolmogorov also had a sophisticated account of conditional probability as a random variable conditional on a sigma algebra. But the point is that something must be done. We can't retain the Bayesian orthodoxy in the face of such cases, and we have to assess the costs of these other approaches. And then there are just other, I think, less familiar problems with Bayesian orthodoxy. So let's now turn to the next weirdness about 0. It's the multiplicative destroyer. Multiply anything by it and you get 0 back, as school children will tell you. And this spells trouble for the usual definition of probabilistic independence. So we want to capture the idea of A being probabilistically uninformative about B. And we're told, just consult any textbook, A and B are said to be independent, just in case you have this nice multiplication, this nice factorization. The probability of A and B is the product. Probability of A, probability of B. According to this account of independence, anything with probability 0 is independent of itself. 0 equals 0 times 0. But surely identity is the ultimate case of probabilistic dependence of the kind that we were trying to analyze. Remember, uninformativeness was the notion of independence we wanted. Suppose you're wondering whether the coin landed heads on every toss in that infinite experiment. We're imagining it's finished. Maybe you've got some big prize resting on it, maybe $1 million, if in fact it's heads forever. And then suppose I know the result and I give you the following bit of information. Oh, by the way, the coin did land heads on every toss. But can you tell me with a straight face that that's utterly uninformative regarding the proposition of interest to you? Heads on every toss. No, nothing could be more informative than your learning that that's exactly what happened. The coin landed heads on every toss. But according to this account of independence, the coin landing heads on every toss is independent of the coin landing heads on every toss. And that just seems like a counterexample. And more generally, according to this account, any proposition with probability 0 is independent of anything that includes its negation, anything that entails it, anything that it entails. And I just want to say, wrong, wrong, wrong. Now, the ratio account of conditional probability was guilty of what we might call a sin of omission. There were cases where we wanted it to speak and it was silent. But this account of independence is guilty of what I call a sin of commission. There are places where it speaks and we wish it would shut up. It's saying that heads forever is independent of heads forever, when obviously that's not right. So I think we need to rethink probabilistic independence. Brandon Feitels and I argue that we should define it in terms of Popper functions. Remember, those were the primitive conditional probabilities. Or something, but not just that vanilla multiplication formula. Next weird fact about zero, it's the additive identity. So while zero is the most potent of all numbers when it comes to multiplication, it's the most impotent when it comes to addition and subtraction. It's the additive identity. Adding it to any number makes no difference, as school children will tell you. I wish those school children would shut up. Anyway, this creates problems for decision theory, I say. Now, arguably the two most important foundations of decision theory are the notion of expected utility and dominance reasoning, and this may be familiar to most of you, but just quick rehearsal. Expected utility is a measure of how good an option is. It's the weighted average of the utilities, the payoffs, associated with that option in each possible state of the world, the weights given by the probabilities of those states. And weak dominance reasoning says if one option is at least as good as another in every possible state, and it's better in at least one possible state, then it's preferable. And here I'm assuming independence of options and states. And normally these rules agree. So here's a game we'll play. We toss a fair coin. If it lands heads, I give you $1. If it lands tails, you give me $1. How good is the gamble from your point of view? Its expected utility in dollars is, all right, well, it's just the weighted average of the payoffs, 1 and minus 1. Minus 1 is the loss of $1 to you. The weights of the probabilities, half-half. The answer is 0. And that corresponds to the intuition that this game is fair. That's the same as the status quo. So you could rationally play the game or rationally turn it down. You have a tie, is the thought. Now, let's change one of the payoffs. We'll sweeten the game for you. If the coin lands heads, I give you $2. It's a bit better than before. Same if the coin lands tails as before, you give me $1. And now the expected utility is this weighted average. Payoffs are 2 and minus 1. Weights half-half. The answers are half, and that's better than 0, which we had before, corresponding to the intuition that this game is favourable to you. You should play it, given the chance. And dominance reasoning agrees. This game is better, and so does common sense. So far, so good. Well, now the trouble. Probability zero propositions show that expected utility theory and dominance reasoning can give conflicting verdicts. Suppose that two options yield the same utility except on the proposition of probability zero. But if that proposition is true, option 1 is far superior to option 2. Suppose we toss the coin infinitely many times. You can choose between these two options. 1, if it lands heads on every toss, you get $1 million. Otherwise, you get nothing. Option 2, you get nothing. Which is better? Well, expected utility theory says these options are equally good. They both have an expected utility of 0. Dominance reasoning says that option 1 is better than option 2. Which is it to be? So 2 points. For a start, these rules are disagreeing. So something's gone wrong. But secondly, I say intuition tells us, indeed yells at us, that option 1 is better and that expected utility is just getting this wrong. So I think that's a counterexample to expected utility theory as it's usually understood.
If you're going to be around for an infinitely long time.
Well, yeah, this is a thought experiment. And we can come back to this about sort of the practical utility of these points. But I'm making a theoretical point. Now, let's start connecting this to AI. In fact, it's good that you spoke just then, because this is the first point of contact. My bet is that the best future AI will use broadly Bayesian techniques. And now, here I immediately concede, to be sure, the problems that I've raised up to this point are only theoretical. I doubt that they'll have practical ramifications for AI. And in Dave's terminology, AI plus and AI plus plus and so on may not have to worry about these probability zero events. I'm just happy to concede that. They nonetheless remain as foundational philosophical problems. I'm a philosopher. I care about the foundations of probability. And for what it's worth, I hope that AI plus and AI plus plus will be philosophically inclined and care about these things too, care about the foundations. Anyway, so much for the zeros. Now, remember my taxonomy? We move on to the next category of improbable events. These are the infinitesimal probabilities. Now, you might say to these examples, like heads forever, or the dart landing exactly on a particular point, really, the probabilities are not zero. They're close to zero, but they're infinitesimal in that technical sense. And you might appeal to some sophisticated number system, the hyperreals, or maybe the surreals, to get your infinitesimals. And so now the picture is like this. If you like squeezed between zero and all the positive reals, you've got this whole rich structure of infinitesimals. And the probabilities that I've been talking about are really taken from there. Well, we may say that the probability that the coin lands heads forever is not really zero, but rather an infinitesimal. Lewis would say that. He's a friend of open-mindedness, remember? And it's through infinitesimals that he thinks he can uphold that friendship. Well, can we really uphold open-mindedness? Williamson has an argument that the probability of heads forever really is zero, even allowing for infinitesimals. I'm happy to talk about that later. I'll just record this. And here's my preferred argument why you really have to close open-mindedness. Even if you allow some richer probability function, like a hyperreal valued function, which also takes on infinitesimal values, still there'll be a problem. You enrich the probability function, you now have a richer range, say hyperreals. I say, if you can enrich the range, I can enrich the domain. Now let's enrich the space of possibilities. Previously, the dart was thrown at the 0-1 interval of the reals. Now I'm going to throw it at the 0-1 interval of the hyperreals. Now here's a picture of that. So I want you to stare at this point x, which is now a hyperreal point in that interval. And we're going to think about the probability that the dart lands exactly on x. And suspense mounts, and whoa, there it is. Amazing. So, what's the probability of what just happened? All right. Each point x, stare at x, is strictly contained within nested intervals of the form x minus epsilon on 2, x plus epsilon on 2. So, centered on x with epsilon. And we know what the probability of one of those is. It's epsilon. For each epsilon, for each infinitesimal epsilon, we have an interval like that. The probability of the interval is that of its length, is its length, which is epsilon. So the point's probability is bounded above by all these epsilon, and thus it must be smaller than all of them. And that means zero, and I really mean zero, I don't mean infinitesimal. So just to say that in one other way, suppose for reductio that the probability of x was some bigger number than zero, and maybe call it delta. Okay? Well, we could find an interval covering x whose probability is smaller than delta, say delta on 2, an interval of that probability, and so on. So delta would be too big for the probability of x. It'd be bigger than an interval covering it.
In effect, you've got x over Adolf naught, haven't you?
Well, yeah, this is tricky when you now combine these cardinal infinities like Aleph naught with the hyperreal infinitesimals. But yes, they don't mix and match so easily. Now, punchline, probability zero events cannot be disregarded by Bayesianism or by probability theory more generally. Again, I'm making a theoretical point. This is not about, something AI is going to have to worry about, as far as I can see. But still, I think it's an interesting foundational point, and I care about the foundations. So we've seen what I take to be some serious vices of orthodox Bayesianism, seen from this foundational point of view, and of orthodox probability theory more generally. One way or another, we need to go unorthodox. So I'd like to think that AI+, and so on will be unorthodox Bayesians. Okay, that concludes that section in the taxonomy. And now we keep marching. And the next category was the real valued small positive probabilities. And now there's nothing weird about their mathematics. It's numbers like 1 in a million. The school children aren't going to say anything now. But still, they give rise to a host of philosophical problems in their own right. And I'm going to raise some troubles for what we call counterfactuals. These counterfactuals are a species of conditionals, so they're if-then statements, and they're typically expressed using the subjunctive conditional. If it were the case that A, then it would be the case that B. Or if it had been the case that A, then it would have been the case that B. And counterfactual reasoning typically involves entertaining hypothetical states of affairs, non-actual states of affairs, imagining what would happen if things were different in some way from how they actually are. We often use counterfactuals in conversation and in science. We can use counterfactuals about the past to account for our feelings of relief or regret. Actually, I nearly did get lost coming here. I went for a cup of tea and then I got sort of stranded in some other building of RMIT. If I'd got lost coming here, then I would have been late for this lecture if I got really lost. Well, I didn't get really lost. I didn't get seriously lost. I made it. Phew. If I'd sold my shares earlier, then I would not have lost so much money. Right? There's a regret of mine, captured by a counterfactual. Sometimes when I psychoanalyze myself, I think what I'm about to argue, most counterfactuals are false, stems from my almost unlimited capacity for regret. I need to find some way to make these counterfactuals that inform my regret go false. Well, I found a way. Anyway, we'll see that shortly. Counterfactuals are often involved in causal claims. If I were to let go of this pen, it would fall. But if I were not to let go of it, it would not fall. Well, that seems to imply that letting go of the pen causes it to fall. They're often used in decision-making. If I were to take my umbrella, I would stay dry. Imagine it's a rainy day, but if I were to leave it behind, I would get wet. Well, that's a reason to take the umbrella. I don't like getting wet. It's counterfactuals informing my decision-making. So as such, counterfactuals play an important role in AI. Presumably they will do so in the future. But I say we have to be careful about which counterfactuals we consider, because I will now argue that most counterfactuals are false. And I hope this strikes you as a surprising claim. I don't want this to be obvious. So I'm saying things like, if I were to let go of this pen, it would fall. False. If I were to jump, I would come down. False. All right, so I hope you see that this is a somewhat radical thesis, but here we go. Most counterfactuals are false. Stare in the face of chance. Picture as vividly as you can what a chancy process is like. And for definiteness, let's make it the toss of a coin, the coin in my pocket. But I will never toss the coin. What would happen if I were to toss the coin? Well, obviously, if the coin were tossed, it would land heads. No, okay, that's a joke. That's silly. I submit that that's false. There's no particular way that this chancy process would turn out were it to be initiated. In the words of Jeffrey, a great Bayesian, that's what probability is all about. To think that there's a fact of the matter of how the coin would land is to misunderstand chance. It's to second guess the outcome of a chancy process. And I say the argument goes through whatever the chance of tails, as long as it's a possible outcome. So now make the coin highly biased. 99% chance of heads, 1% chance of tails. Still I say it's false. To say, if I were to toss the coin, it would land heads. It might not. There's a chance of tails. It might land tails. That's what chance is all about. Even when the chances are skewed. Or consider a fair lottery, talking about skewed chances. If you were to play the lottery, you would lose, I say is false, no matter how many tickets there are in the lottery. So consider a particular large lottery, say 1 million tickets. Suppose you think this counterfactual is true. If you were to play the lottery, you would lose. Okay? Then you'd better say that if you were to play the lottery, ticket number 1 would lose, just by the symmetry of the case. You don't have any special reason to disfavour your ticket. It's not like your ticket is especially unlucky or something. Whatever you say about your ticket, you'd better say of ticket number 1. It would lose. Okay? How about ticket number 2? Oh, it would lose. You're committed to saying that. ... all the way up to the 1,000,000th ticket, it would lose. Now hang on. You agree that there would be a winning ticket, but you've just told me that each ticket would lose. In an indeterministic world such as ours appears to be, lotteries in a broad sense abound. Appears to be. Well, the evidence from quantum mechanics points that way. It doesn't completely guarantee the point. And I don't just mean the canonical quantum mechanical cases of indeterminism, radioactive decay, or spin measurement in a Stern-Gerlach apparatus. Not just those are indeterministic. We're told that the indeterminism even reaches macroscopic objects, just less obviously so. So imagine, say, a billiard ball, the cue ball approaching the 8 ball. That approximates a deterministic system, but even it is not immune from the quantum mechanical effects. The cue ball could spontaneously quantum tunnel through the 8 ball, or to China, or to the North Star. Or a human jump. Suppose you jump. Well, there's some tiny chance, I know it's tiny, but some chance of my not coming down. It might vaporize instead, mid-jump. So in this sense, billiard ball collisions, human jumps and so on are indeterministic. Subtly so, the chances associated are extremely tiny, but they're non-zero. So I say, if I were to jump, I would come down. That's false. Now, in case you think I'm crazy, to be sure, a closely related counterfactual is true. If I were to jump, I would very probably come down. That's true. But I say the probabilistic qualification makes all the difference. To ignore it is to make a Cournot-like rounding error. Remember, he's the guy who said low probability events will not happen. And Aristotle and Tim Minchin refuted him.
So you don't want to say, if I were to jump, I would come down is probably false. You're putting the probably somewhere else.
Good point. Now, I would say it's definitely false because of the argument I've given you. What is true is if I were to jump then, and here comes the probably, just as you said, probably I would come down.
So you don't like possible world semantics?
That's right. You're quite right. I mean, we could have a nice talk about that. I don't know if that immediately follows from what I've just told you. I think you could square what I've said so far with possible world semantics. If you somehow say that when you look at the closest worlds, among them will be the anomalous ones, like my coming down, because it's like a lottery. Just like in a genuine lottery, each ticket's winning is, so to speak, equally distant.
It'll be hard to get it totally false using possible world semantics, I would think.
No, well, I think it would be, at least on the Lewisian account, it would be pretty easy, as long as there's at least one closest antecedent world where the consequence is false. But I'd be glad to talk more, because that's very relevant to my project. Anyway, well, there are various reasons why you may not be staring chance in the face. Maybe you don't know about the relevant physics, for example, the relevant quantum mechanics. Or maybe you do, but you're just somehow not thinking about it. Or maybe you're just consciously trying to ignore it, the way you might try to ignore an annoying TV commercial, even when it's right there in your face. For whatever reason, you may not be staring chance in the face. The trouble is that chance is staring at you. It doesn't go away just because you don't know about it, just because you're not thinking about it, just because you're trying to ignore it. You know, the physics is staying constant as a backdrop all along. Chance is heedless of your ignorance, defiant of your ignorings. Once you take seriously what quantum mechanics says, you should see chanciness almost everywhere. The world looks like a huge collection of lotteries. Highly rigged lotteries, to be sure. Lotteries with many, many tickets, to be sure. But that isn't relevant to the point about the counterfactuals. But whether or not you take seriously what the theory says, that's apparently how the world is. All right, so that concludes that section. Now I want to move on to a different kind of motivation for the improbable. And this is one that comes from multiplication by extremely large utilities. So even extremely small positive probabilities can be offset by multiplication by extremely large utilities when calculating expected utilities. Remember, you do that multiplication of utility and probability when you add. And the poster child for this is Pascal's wager. Pascal argued as follows. Here are two ways that the world could be. God exists, God does not exist. And you will not be able to figure out how the world is just by thinking hard. As Pascal says, reason can decide nothing here. But he thinks reason can decide something else. What should you do? And this is a matter of your attitude to God. Should you believe in God or not? This is something you can choose, thought Pascal. Or in his language, you could wager for God, think of that as belief, or wager against God, think of that as non-belief. And here are the associated payoffs. So, according to Pascal, if God exists and you wager for God, you get salvation, you get infinite utility, as he put it, an infinity of infinitely happy lives. It's like Collingwood just winning the premiership infinitely often. Now, in every other case, you have your finite earthly life and then you die and that's it. And the utilities are all finite, which I'm designating with these Fs. Finite, finite, finite. So I don't need to specify those numbers. Further premise, your probability that God exists should be positive. It may be very small. It may be 1 in a million, 1 in a Googleplex, but it should be positive. And remember what I called open-mindedness. That would actually entail it has to be positive. Further premise, you should maximize expected utility. This we recognize from decision theory, and heaps of credit to Pascal. He was just one of the pioneers of decision theory, and in fact it's said that Pascal's wager was the first ever decision problem solved with the techniques of what we now call expected utility theory. Therefore, you should wager for God. And let's just do it slightly more formally and carefully. Let P be your positive probability for God's existence. Your expected utility of wagering for God, well, now it's a weighted average of the payoffs infinity and this finite thing, F1. And the weights are P, 1 minus P. And that's infinite. It's a weighted average of infinity and something finite, which is infinite. And your expected utility of wagering against God, well, now it's the weighted average of F2 and F3, which were both finite, and it doesn't really matter because the answer is finite. Infinity is bigger than finite. You should maximize expected utility, therefore you should wager for God, Pascal's wager. Could a machine enjoy infinite utility? That infinity, Pascal really had this thought of us, being human and having a soul and so on, and it's something that we could raise, whether a machine could really face that decision matrix. And as well as the intelligence explosion, central to the singularity discussion, we could imagine a utility explosion, like machines building machines with greater and greater capacity for happiness. Like U plus, okay? Explosion of these receptacles of joy. Could we reach a utility singularity? Here I'm reminded of Nozick's utility monster. This was an argument of Nozick's against utilitarianism. There could be this sort of utility sink, this agent that gets such value out of things that it just sucks up all resources. That's the right thing to do with resources. Give it to the utility monster. Anyway, never mind that. Pascal's argument is simply invalid. So let's just grant Pascal all his premises. Grant him that decision matrix. Grant him positive probability for God's existence. Grant him expected utility theory. Doesn't follow that you should wager for God. Pascal specious steps to assume that only the strategy of wagering for God gets the infinite expected utility. He's ignored all the so-called mixed strategies. So these are ways of coupling what you do with the result of some process that you regard as chancy, probabilistic. So to see the problem, consider this mixed strategy. Toss a coin. If it lands heads, wager for God. If it lands tails, wager against God. So notice this is not Pascal's recommendation. But let's figure out its expected utility. According to Pascal, and remember I'm just granting him his premises, the expected utility of this mixed strategy, well, it's a weighted average of infinity, that's what he got from his calculation, and some finite value, according to the probabilistic weights of the coin toss, half, half, and that's infinite. The same as that of outright wagering for God. We have a tie in expected utility. And then when you see the problem, you just see it everywhere. So consider this mixed strategy. Wait to see if your lottery ticket wins. 1 in a billion chance that it does, say. If it wins, wager for God. If it does not win, wager against God. And according to Pascal, the expected utility of this mixed strategy, all right, well, the weights, the utilities are infinity and some finite value. The probabilities are 1 in a billion and 1 minus that. And again, that's infinite. I'm just using his very numbers, his premises. Or consider even more esoteric mixed strategies. For example, wager for God, if and only if I quantum tunnel out of this room before the end of this talk. There's some positive probability of that. Low, I hope. Multiply that probability by infinity and you get infinite expectation for that mixed strategy. But this still understates Pascal's troubles. For whatever you do, you should apparently assign some positive probability to winding up wagering for God. So suppose you don't want to think about all this wagering, you just want to have a beer. Well, there's some positive probability that while you're having the beer, you'll have an epiphany. You'll end up wagering for God. And then according to Pascal, you enjoy infinite expectation. Okay? Multiply the probability of the epiphany by infinity. You get infinite expectation for the beer. Beer's good, it's not that good. Suppose you do all that you can to avoid wagering for God. Maybe you start worshipping the devil. Maybe you try to attempt suicide just to render yourself free of all beliefs. Still, there's some probability positive that you will fail in this endeavour. You'll wind up wagering for God nonetheless. Multiply the probability by infinity. You see how this goes. So do you see how bad the problem is for Pascal? Literally, anything you might do gets the same infinite expected utility. And those were the lights by which you were supposed to judge what you do. Well, if you're open-minded in that technical sense, you assign positive probability to all such non-Pascalian routes to wagering for God. It's not impossible that you will have an epiphany while drinking the beer. By open-mindedness, you must give it positive probability. Multiply that by infinity. So Pascal's utility matrix implies that everybody who's open-minded enjoys maximal expected utility at all times. You know, Leibniz said that this was the best of all possible worlds. I don't think he had that in mind. Well, so far I've been, so to speak, laughing at the trouble that Pascal gets himself into. He now gets his revenge. He has the last laugh, back at me. See, previously I granted Pascal all his premises. Now I won't. I don't believe the conjunction of Pascal's premises. In fact, I only give small probability to the conjunction of Pascal's premises. But hang on, still the problem that I displayed for him now hits me with full force. With tiny probability, I enjoy maximal expected utility at all times. But that means that by my lights, even though I give small probability to his premises, I actually enjoy maximal expected utility at all times. But this still understates my troubles. For whatever I do, I should apparently assign some positive probability to winding up believing Pascal's premises, or even just assigning them tiny positive probability. I think I'll just go over beer. No, even that won't save me, because there's some positive probability that I'll wind up believing his premises. And away we go. And likewise if I try to avoid belief. But don't mock me, you're in the same predicament, or should be. I mean, you could avoid the predicament by assigning probability 0 to the conjunction of Pascal's premises, and to all ways of coming to assign positive probability to them. But are you rationally entitled to be so dogmatic? Well, open-mindedness requires you not to be. And maybe even AI plus and AI plus plus will be required to assign positive probability to these things. And I think I've about 5 minutes left. Is that okay? So that's about where I'm good. Now, Pascal's wager can apparently be made valid. So remember that figure 8 infinity, that bow tie infinity? Replace it with a finite but really big value. Let's call it f. And just rerun the calculations, but now with big F replacing infinity. How big is big for f? Well, large enough so that that first calculation is bigger than the second. And we can always find an f finite that's big enough. And some real-world decision problems look rather like this because they involve sufficiently high stakes relative to the associated probabilities. Consider moral uncertainty. So I had a nice steak. I like my steaks. But I worry about this kind of reasoning. Maybe eating meat is wrong, and I mean really wrong, somewhat akin to murder. I don't believe that. In fact, I only assign tiny probability to that being true. But still, if I attach sufficient disutility, I'll mark that with a -f to remind you of the negative aspect of it. Then, doing the calculations, it looks like maybe I should not eat meat because I attach sufficient disutility to getting it wrong in that sense, doing something akin to murder as it might be. Well, one could ask whether AI++ and so on will be uncertain about morality. Dave talked about the possibility of a morality explosion leading to a morally perfect singularity. We could ask, if so, how will it make morally charged decisions? Or with its superior intelligence, will it have no difficulty determining the correct moral theory and the correct course of action? Well, those are hard questions. And then the last bit in my taxonomy, this is really quick, this is just 3 minutes. Suppose our probabilities are imprecise. Remember, that was the fourth category. Due to some lack of relevant information or conflicting information. And as before, think of these imprecise probabilities as interval valued with a small upper limit. But when the associated stakes, not in the sense of the meat, but the payoffs are sufficiently high, there may still be cause for serious concern. That was this unpronounceable Icelandic volcano. All of Europe's airports closed because of the risk to flights posed by the eruption of the volcano in Iceland. We were told by the aviation officials the probability of crashes was small. It was also imprecise. They just couldn't put a number to it. But the stakes were so high that it was wise to cancel the flights. I'm happy to concede that. And now I think the point I've just made about flying there could carry over to the singularity. So we've heard arguments that we should regard the singularity as probable or likely, or you should expect it. Even if it's improbable, we should take it seriously since the corresponding stakes are so high. And it's presumably rational for us to assign it imprecise probability. I can't stick an exact probability sharp number to it. But even with a low upper limit on this probability, the prospect of it may play a significant role in our decision-making. And future AI, in turn, will presumably be uncertain about various things. It'll be intelligent, but not omniscient. It may well use imprecise probabilities. They're becoming increasingly important in AI. Future AI may have to take low probability events seriously when the corresponding stakes are sufficiently high. And it may need to be especially good at computing just how high the stakes are. Okay, and then this is the very final case in which the themes of the improbable, the imprecision, high stakes, and morality all come together. And this is global warming. Climate scientists differ in their probabilities of various scenarios of global warming. This is just lack of information leading to conflicts. And it seems that our probabilities should be correspondingly imprecise. So here is a graph showing different scientists giving different probabilities over various global warming scenarios. Along the horizontal axis, we've got various scenarios. Think of these as warming by the end of the century. That simplifies, but it's close enough. Like 1 degree average warming, 2 degrees, ever worsening scenarios. And then various scientists putting their probability density functions over these scenarios. Notice they're differing, the scientists, they're given different curves. Faced with that, I just go imprecise. I'm no scientist in climate change, so just that sort of band of probabilities corresponds to my own. the probabilities are centered, they hit their peaks somewhere around 2 degrees, I guess, perhaps somewhere around here, 2 to 3 degrees or so. And that's how the debate is normally couched. We mainly hear about the most likely scenarios, which involve serious consequences, but various people argue that they're not catastrophic. 2-degree warming, well, not so good for the Maldives, but life could go on recognizably as before, they say. But perhaps we should be rather more concerned with much less likely scenarios, but ones that involve truly catastrophic consequences. Here I take my lead from people like Weizmann and Broom. And this is so even when the corresponding probabilities are imprecise. So when I look at these curves, so I'm worried enough about what I see here, the 2-degree scenarios. But in a way, what I'm really worried about is what I see down here, at 10 degrees and beyond. And we still have these climate scientists giving positive probability to these extreme scenarios. No one can claim these are life recognizably as before scenarios. This could well be the end of the human race beyond there. You can't quite read the numbers. It's a bit hard to read the curves. But the bottom of these probabilities there is about 1 in 100. Probability 1 in 100 for this high impact event. 1 in 100 is 1%. So even he should worry about it. Thanks a lot.
Do you have some questions?
Yeah, you bet.
Okay, any questions? Colin was the first with his arm raised.
Alan, could you go back a couple of slides to Pascal's table, please?
Yep. It's probably a faster way to do this, but it'll get there. And do you want the original Pascal table?
That'll do.
Oh.
No, the one with
One.
non-existent doesn't.
That'll do, yep.
That'll do. That betting situation has been wrongly framed, I think you'll agree, that in Pascal's time, the 2 columns should be called a Catholic God exists, or Catholic God doesn't exist, that was his era.
Yeah, fair enough.
In fact, there are almost an infinity of columns going up to the right for the millions of pagan gods that exist, and he didn't properly bet on them.
Yep.
Surprising, since Pascal was the father of probability and gaming theory. Why didn't he bet on the millions of columns over there?
Yeah. So spot on, this is the famous many gods objection to Pascal's wager, which is one of the killer objections also to Pascal's wager. Yeah, so by his own lights, this is your point, he should be entertaining other hypotheses. He's the one who told us reason can decide nothing here, and if you take that seriously, it can also not rule out these various rival gods. So yes, he did have in mind this Catholic conception of God. He was writing to a certain audience, in sort of Catholic times in Catholic France.
Should be betting on unicorns and flamingos.
Yeah, but you're quite right, and gods who punish the believers and reward the non-believers and the whole range. For each real number, the god whose favourite number is that real number. You've got a continuum of gods right there. So that's a serious objection. In a way, that's a sort of counterpart to the objection I raised. The many gods objection, the many sort of strategies objection, right?
It's only a century before.
Yeah, I have a different kind of objection.
Yeah, well, sure, that's true, that's right. He was writing at a certain time in history to a certain audience. You can understand why he framed things the way he did. He was just trying to say to a certain audience who's arguing against him that his belief in God is irrational. Well, how irrational am I? Let's get our best theory of rational decision. It seems to vindicate my belief. But then we've seen the problems. Okay, sorry.
So I want to turn things back a little more toward AI and probability. So in my own AI work, probability is a significant component. But since you like to understand things foundationally, when I look at the foundations of what justifies using probability to manage uncertainty, I find it a bit unsatisfying. You look at, say, Cox's axiom for the algebra of probable inference. which is an elegant justification of using probability theory. But one of his axioms essentially assumes that, I mean, to put it in layman's terms, like if you derive the same conclusion by multiple paths, you'll always get the same answer. And that really doesn't hold for a system with finite resources in general. So if the axioms underlying the correctness of probability don't hold for real systems making decisions in real time with finite resources, what then is the foundational justification that AI systems should use probability theory?
Yeah. Good, that's right. So, I mean, we sort of triangulate to probability theory in various ways, although the point you made about Cox's theorem, you might raise for each of these roots
for the Dutch book,
exactly what I was
saying. You
saying.
can raise the same argument anywhere. And if the wager is too complex, a finite resource system may not have time to puzzle out or that's to make a decision.
Yeah, fair enough. And in fact, I've raised worries myself about some of these routes to Bayesianism and, in fact, the Dutch book in particular. That's all true. And I think you're taking more seriously than a philosopher like me takes, like the constraints of this finite.
Well, because the reasoning is always done by a real system with finite computing resources.
Sure.
So should that finite system use probability, or could there be some other way of managing uncertainty which is actually better for a system with such limited resources, making the decisions it has to make? Does anyone work on that kind of question?
People do, and in the area of bounded rationality and so on. I certainly grant, Bayesianism is up to its neck in idealization, idealization about the agent being logically omniscient, so that's a certain assumption of infinitude. When you take on the full Kolmogorov probability theory, you have infinitude written into one of the axioms. Countable additivity is an infinitary.
Well, so one way to think about it is if Cox's axioms almost held, would probably be almost the right thing to do.
Then it's time to get your epsilons and deltas out and really do the proof. Offhand, it's not so simple, I think.
No, I tried to do that proof, and it wasn't that clear. But
exactly.
Of course, I might not have tried the right way.
Yeah, exactly. So I think it's a really, really good question, and in a way, you're asking why am I so sanguine about this Bayesian future? I mean, you could say that Bayesianism is a good approximation in various ways. Like, when we're at our best, when we're reasoning clearly, when the problem before us is not too complicated, it does seem that we reason probabilistically. It can be well modeled.
Well, I'm not sure that we do, but you could say we should, and we're able to. But those cases involve a fairly small number of variables, which is quite different than the default case of what human beings need to do, which involve a huge number of variables that strain our computing resources. Also, I mean, idealization is well known in science. Physics is up to its neck in idealization. Economics is up to its neck in idealization. And in fact, often in exactly these ways, idealizations of infinitude, infinite space-time curvature is possible. Economists like to imagine infinite, societies with infinite capacity for utility. And yet, a lot of this theorizing seems to go pretty smoothly, and it has some practical benefits. So sometimes the idealization actually is in the service of delivering a useful theory. And now I guess it's an interesting question. To what extent is that true of Bayesianism with its infinitude idealizations, and even before you get to infinitude?
I take it that from your lecture you're making an analogy between Pascal's wager regarding belief in God and our wager, if you like, regarding belief in singularity. Is that a fair assumption? That
is a good way to put it. And while I argued against Pascal's wager in its original form, remember I just replaced the infinity, which was so problematic, with the big F, the high stakes but finite. That probably approximates more the situation with the singularity. High stakes, there's a big F, so to speak, associated with the singularity coming to pass. So this is just to add the detail to the arguments that you should actually expect the singularity. Dave went through such arguments, for example. even if you shouldn't expect the singularity, even if those arguments don't go through, just small probability of the singularity requires our serious attention.
Well, there's one difference, of course, between the analogy is that with Pascal, he could only affect the numerator, the belief side, if you like, not the denominator, the fact side, whereas we can affect both.
I see what you're saying.
And
Yep, good. So,
and also, by the way, it makes me feel a little more sympathetic to Christians when I see that argument, because I can sort of see their point and see that it is obviously a high value outcome. So, which one might help maybe a little sympathy between both sides of that argument.
Yes.
Unless they're voting for a punitive God.
So you made a good point that here, presumably, we don't have any influence in the states of the world. It's just a given, and it's outside our control whether God exists or God does not exist. And I think your point is it's not like that with the singularity. And we have some input into whether it happens or not. And this resonates with stuff that Dave said about various defeaters of the singularity. Like, we could decide not to let it happen if, for example, we think that its consequences would be too bad. So there is that, but I still think there is this sort of decision theoretic aspect to it. High stakes if it happens, right? Even if the probability of it's small. And by the way, we could decide, not to let it happen, and still it happens, because whatever, there's a defector amongst us. Okay? Still, I think we should agree there's some low probability of it happening, even if we try to stop it. And then this sort of Pascalian reasoning kicks in again. Because the stakes are high. Yeah.
I take it you're not an atheist. That's
a whole other topic. I'm not persuaded by Pascal's wager. I will tell you that.
Okay. Yeah, I was just wondering, you were talking about treating seriously high impact but low probability events. My only concern with that was that there seemed to be a very large number of low probability high impact events. It's very easy to come up to. Just as an example, when the LHC was about to be over, there was concern about it creating a black hole and devouring the Earth or something like that. And people said it's almost certainly not going to happen, but there's some finite probability it's going to happen, and then therefore you should take it seriously. It just seems very easy to come up with sort of any random thing that's high impact but very low chance. I just wanted to comment on that.
That's right. Here's the example, right? The super collider. That was the one you had in mind. So I thought about that so much that I prepared a slide in anticipation of it. So just to walk you through this quickly, I think you're raising a version of this worry that this is like a plea against the improbable. It's if you dignify every high-stakes, low-probability event with your attention, well, various bad things, you'll live in constant fear. Everything you might do has some positive chance of dire results. You'll be pulled hither and thither. You'll be paralyzed in this sense. And this is related to what I said about AI++ and so on, needing to really get the utilities refined. We're not terribly good at figuring out just how bad are the payoffs or how good are they in these various scenarios. I mean, I'm tempted to bite the bullet and walk through the list of nightmare scenarios and, to the best we can, try to assess their probabilities imprecisely, to be sure, I've said that, and do our best to figure out the utilities to act accordingly. Now, I'm glad you raised that very example, the super collider. That probability really was small. They calculated it fairly accurately, I guess, and it was really small. And it was nothing like the 1 in 100 chance of the 10 degree plus warming. So certainly I won't worry about the black hole the way I'll worry about global warming. And this is a whole big topic about how we are to handle these sort of low probability, high stakes scenarios. One way is to develop strategies that you might call robust. So dealing with many scenarios at once. For example, building refuges, coordinating disaster response and so on. In a sense, like handling many high-stakes scenarios simultaneously. And
dog-minded service. A dog-minded service.
Okay, yeah, I know what you mean, that's right. And finding techniques for estimating probabilities better, like maybe pooling probability estimates, taking advantage of the wisdom of the commons. And then finally, and I'll finish with this. What?
Microphone.
You're right on top of the microphone.
For me?
Bloody edges.
Don't worry. And also, I think it'd be useful to do various value of information calculations. So, for which things would it be especially important to have knowledge of the relevant probabilities? Maybe a good example of this is the probability of asteroid collision. So, people in the know of this tell me it's relatively low cost to get the information and potentially huge benefit in having it. So maybe that's the sort of thing we could target our resources to.
Okay.